All right, let's dive right into one of the most powerful and honestly mind-bending technologies in modern crypto, zk-SNARKs. This stuff is seriously changing the game for everything from scaling blockchains to how we prove who we are online. So it all starts with a question that sounds like a total paradox. Imagine you have to prove you know a secret, like a password, to get into a system. But here's the catch. You can't actually send the password. So how do you prove you know it without, showing it? That's the exact puzzle zk-SNARKs were born to solve. To get our heads around how they pull this off, we first need to understand the fundamental idea they're built on, and that's something called a zero-knowledge proof.
At its core, a zero-knowledge proof does exactly what it says on the tin. It's a method where a prover can convince a verifier that something is true. And that is absolutely it. The verifier learns nothing else. Not the secret, not the underlying data, zilch.
Now, for this digital magic trick to be trustworthy, it has to follow 3 unbreakable rules. First, completeness. This just means if you're telling the truth, the proof will always work. Simple. Second, soundness. This one's critical. It means a cheater can't fake a proof and fool the system. And finally, the star of the show, zero knowledge. This guarantees that your secret always stays secret. Okay, so that's the theory. But how does a computer actually make one of these things? You can't just run normal computer code. First, you have to translate that program into the pure language of mathematics. This whole translation process has a fancy name, arithmetization. Think of this process like a complex translation engine. It happens in 3 main stages. First, flattening takes complicated code and smashes it down into really simple steps, like basic addition and multiplication. Next, R1CS turns all those steps into a huge web of mathematical constraints, kind of like a giant Sudoku puzzle. Finally, and this is the really clever part, a technique called QAP takes that entire puzzle with its millions of pieces and compresses it into a single, elegant mathematical equation. That final step is what makes the proofs so small and fast to check. So the takeaway is simple. We're turning human-friendly code into pure math. Now, this all sounds pretty amazing, but the early versions of these systems had a huge security asterisk attached, and it all came down to a critical vulnerability in how they were first created. This vulnerability was given a pretty dramatic name, toxic waste. It's the secret, random data that's used to generate the system's initial parameters. The problem? If anyone who helped create the system held on to that secret data, they'd have a master key that could break everything. And the stakes here are absolutely massive. In a cryptocurrency like Zcash, for example, someone with the toxic waste could just create fake coins out of thin air. They could print money, and the system would have no way of knowing it was counterfeit. It totally shatters that soundness guarantee we just talked about. So the first SNARKs, like Groth16, were super rigid. You had to run this massive, complicated setup ceremony for every single program. And if you changed just one line of code, you had to do the whole expensive thing all over again. But then we got a huge breakthrough with universal setups, like the one used in Plonk. This was a game changer. You do one ceremony, and you get a set of parameters you can reuse for tons of different applications. Much better. So once the trust model started getting better, the next big hurdle was performance. Actually generating one of these proofs can be incredibly slow. This kicked off a full-on arms race for speed, a race that has moved from clever software tricks all the way to designing custom-built computer chips. You can really see this evolution in the protocols themselves. Groth16 is still the undisputed king of tiny proof sizes, which is great, but it has that annoying circuit-specific setup. Plonk gave us the universal setup, which was awesome, but the proofs got a little bigger, and then came the really big leap with protocols like Halo 2, which are transparent. That just means they need no setup ceremony at all. The toxic waste problem is completely solved. The trade-off? The proofs get a bit larger still. And that brings us to the other main technology in this space, SNARKs. This chart really lays out the rivalry perfectly. SNARKs have those beautifully small proof sizes, which is perfect for blockchains where every single byte costs money. SNARKs, on the other hand, are transparent by default, and, get this, they're resistant to quantum computers, which makes them incredibly future-proof. The downside? Well, look at the proof size. They're way bigger. So, about that arms race for speed, this chart says it all. Trying to generate a proof on a regular CPU is our baseline. It's slow. If you use a powerful graphics card, a GPU, you get a significant speed up. But the real game changer, the massive leap forward, comes from specialized hardware, ASICs. These are chips designed to do one thing and one thing only: generate ZK proofs at lightning speed. And let's be clear about what we mean by a leap forward. 97 times faster. That's not just a small improvement. It means a specialized chip can be done generating a proof in the time it takes a high-end CPU to just get started. This is the kind of massive performance boost that unlocks real-time, seamless applications. With that kind of speed now possible, zk-SNARKs have officially escaped the laboratory. They're out in the wild, being used in real-world applications that millions of people interact with every day. Let's look at where they're making a real impact. Right now, the biggest job for SNARKs is scaling blockchains. ZK rollups, like the ones from zk-SNARK and Polygon, are a perfect example. They bundle thousands of transactions together off-chain and then post just a single tiny proof back to Ethereum. The result? Transaction speeds can go up over 100 times, and fees for users drop dramatically. But it's not just about making things faster. SNARKs are also fueling a revolution in digital privacy. Zcash uses them to make transactions private. WorldCoin uses them to prove you're a unique human without anyone ever seeing your biometric scan. And projects like zk-Pass let you prove things about yourself, like that you're over 21, without having to hand over your actual ID. So where is this all going? Well, if you think things have moved fast so far, you haven't seen anything yet. The pace of research is actually speeding up, and we're on the verge of the next wave of breakthroughs. We're seeing brand new ideas emerge like Lasso and Jolt, which are totally rethinking the proving process to make it radically more efficient. And then you've got amazing stuff like Binyas, which works with individual ones and zeros instead of big numbers, cutting out a ton of wasted computation and making proofs even faster. The end goal for all of this research, from the crazy new math to the super fast custom hardware, is to create something called the invisible prover. A world where generating a proof is so fast, so seamless, that it just happens in the background. As a user, you won't even know it's there. It will just work. And that really leaves us with one final huge question. In a world where you can prove anything you need to instantly, and where your privacy is guaranteed by mathematics, what new things become possible? What new applications can we build? What new ways of interacting with each other can we design? The potential is truly staggering.